thermal structure of northeast Japan subduction zone, a perspective from dehydration-induced earthquake hypothesis.
Thank you, Chairman, and thank you for organizing committee for giving us the opportunity to give a talk in such a nice meeting. Okay, I continue the topics given by Omori-san, and I'd like to talk about the thermal structure of Northwest Japan subduction zone determined on the basis of the dehydration-induced earthquake hypothesis. As Omori-san already explained, the dehydration-induced earthquake hypothesis had been proposed many decades ago, and somebody believes as a main cause of intraslab earthquakes. And based on this hypothesis, the essence of this hypothesis is like this: that hydrous minerals included in subducting slab decomposes at a certain pressure and temperature conditions and releases aqueous fluids, and that liberated aqueous fluids may reduce the lithostatic pressure in surrounding matter, and that promotes brittle fracture and causes earthquakes. I don't like to discuss whether this hypothesis is true or not, but I'd like to use this hypothesis as an indicator of temperature in the slab, because if this hypothesis is true, we can assume that the locus of dehydration corresponds to the locus of seismicity in the slab. And we will know the temperature conditions of dehydration. I mean, we know the stability fields of hydrous minerals in the subducting slabs. So if we can link these two phenomena, we can determine the pressure temperature conditions of seismic zones in the subducting slab. And so the purpose of our study is to determine the thermal structure of the subducting slab and mantle wedge if possible, just on the basis of the dehydration-induced earthquake hypothesis. So we only depend on the seismic observation and petrologic constraints to determine the thermal structure. And we don't depend on the numerical simulation. This is our motivation to do this work. And another purpose is we want to know the logical consequences of this hypothesis. So if you believe this hypothesis, you have to believe our results in theory. So this is the rationale of our study. So if the hypothesis is true, we can assume that the locus of dense seismicity in the subducting slab corresponds to the area where fluid will release. That means the hydrous minerals decomposes. So we can, if we draw the boundaries of double seismic zone like this, we can assume that the inner boundary corresponds to the line here on the glacier temperature diagrams, where hydrous minerals start decomposition. So the hydrous minerals start to liberate aqueous fluid. And the outer boundary, the blue line, corresponds to the blue line on the PT diagram, where the decomposition of the hydrous minerals ends. So if draw one line like this, so we can determine the temperature along the inner boundary and outer boundaries. So the temperature of these green points can be can be determined to be T1, and the blue point, the temperature of two blue points should be T2. This is the rationale of our study. And this method can be applicable to both peridotitic part and basaltic part of the subducting slab. But for basaltic part, we have much more complex dehydration reaction, and so we can determine the glaciative temperature path much more precisely than this rationale. So we employed we determined the temperature distribution within slab crust on the basis of the method just explained by Omori-san to match the search for the glacial temperature path to match the distribution of hydration and that of seismicity within slab. And we have determined the temperature distribution of the subducting slab along this section. It's just the middle of the northeast Japan arc. This section goes through the Chokai volcano and Kurikuma volcanoes. And the seismic data we used is the hypocenter distribution determined by double difference hypocenter location method by Kita et al. And phase diagrams we employed are here. For periodized compositions, we modeled these two phase diagrams for normal laser composition and refractory Hertzbergite compositions. These are modeled from thermodynamic calculations and high pressure experiments for simple four-component systems, including MgL, Si, and H2O for both periodized. And for basalt composition, for hydrated mob composition, we modeled the 7-component system. We also used the solidus of wet mob and solidus of wet periodized taken from the literature listed here. And we also employed some other assumptions that the pressure temperature conditions just below the volcanic fronts were taken from the glacial temperature conditions for the genesis of primary arc magmas. It's about 1,300 degrees C at 1 to 2 GPa. As compiled by Grove et al. And the lithology of the slab, subducting slab is assumed to be layered. The uppermost part consists of 7 km basaltic slab. It's a hydrous mob. And the uppermost 10 km thick part of periodized thick part is assumed to be Hertzbergite, very refractory composition. And the rest of the slab is to be laterite. And the lithology of the mantle wedge is the whole part of mantle wedge is assumed to be laterite. And we show the result of our modeling. This is the pressure temperature path of along the surface of the slab and along the 5 km deep within the basaltic part of the slab, determined as by Omori-san as explained in the previous talk. And first, to determine temperature distribution, we first determine the position of the boundary of double seismic zone, like this. Honestly speaking, this procedure is very arbitrary. So anyhow, we determined like this. So we do two boundary lines, and we determine the temperature along these two boundaries, like this, and along the surface and 5 km depth in the slab crust, like this. Also, we put the temperature for the genesis of arc magmas here. Then we do temperature contours like this by eyeball fitting, just eyeball fitting. And so now we determine the the temperature distribution within slab and the wedge, then we can draw the stability field of hydrous minerals within slab and mantle wedge. This colored area is where hydrous minerals can be stable, and I don't mean that this areas are full of hydrous minerals. We don't mean the slab, upper part of the slab is fully hydrated. This shows just the stability. So in the colored area, the hydrous minerals can be stable if there is enough water available. And the important point of this figure is that hydrous minerals within mantle wedge is restricted to the shallower part. And we don't have any hydrous minerals deeper than about 130 kilometer depth. So no hydrous layer in the mantle wedge in the deeper part of the mantle wedge. And this is the locus of fluid release. That means the area where hydrous minerals decompose and release the fluid, aqueous fluid. So in the mantle wedge, aqueous fluid will be released from wide areas. And within mantle wedge, it's difficult to say for the shallower part because if the material goes to upward, then this material will be hydrated. But if the material within shallower part goes down, then it will dehydrated. So it's very difficult to say exactly for this part. But at least within mantle subducting slab and just above the subducting slab, the dragged flow part, the fluid will be released within this full area. And as you can see, this is not restricted to just below the volcanic front. So this means the position of volcanic front is not constrained by the locus of dehydration. And we also draw the area where partial melting can occur in this red hatched area and this purple area within subducting slab. So as you can see, the wide area in the mantle wedge can partially melt if enough water is supplied from below. And also, the slab itself also partially melts in the deeper part. So slab melts with the inevitable consequence of our hypothesis. Actually, in the subducting slab crust, all the hydrous minerals are decomposed around 100 kilometer depth. So the deeper part of the slab crust is actually dry, but the aqueous fluid will be supplied from the below by decomposition of hydrous minerals within peridotitic part of the slab. So, and the more wet soil goes through like this. So within this portion, the slab crust can be melted. Okay, lastly, I like to mention about the velocity contrast of the slab surface recently detected by receiver functions. There's some research, some studies with find a very sharp velocity contrast along the slab surface, like this, and these velocity contrasts usually be interpreted to be the presence of low velocity, very hydrous layers just above the slab surface, like this. And according to our model, it's okay for shallower part, it's shallower than 130 kilometers, there can be hydrous layer in the mantle wedge. But at the deeper part, we have no hydrous minerals in the mantle wedge. So for the depth less than 130 kilometers, hydrous layer, the VRC contrast may show the presence of hydrous layer in the mantle wedge. But for the deeper part, we think the VRC contrast will be made by the partial melting zone along the top surface of subducting slab. So, okay, let me summarize our results. The logical consequences of the dehydration-induced earthquake hypothesis include the several important points. There is no hydrous layer in the mantle wedge, deeper than about 130 kilometers. And fluid release is not restricted below the volcanic front, so the position of the volcanic front is not constrained by position of fluid release. And the partial melting occurs widely in the can occur widely in the mantle wedge and in the slab crust, even in the northeastern Japan arc, where a very old and cold slab is subducting. And of course, we have some shortcomings in our model. The most critical point is ambiguity in positioning the double seismic zone boundary. This time we drew the boundary by just eyeball fitting, but we need more precise method to determine the boundary without any arbitrariness. And we didn't consider the amount of fluid released from the subduction slab. But if the hypothesis is true, we can correlate the amount of the fluid released and the density of hypocenters in the subducting slab. So these points should be improved in the future work. That's all. Thank you very much.
Question?
Yeah, I know there are many double seismic zones exist, so you may look at some others, double seismic zone to fit the line of the double seismic zone, so that you can present more constraint.
So if we can see the clear double seismic zone, we can apply this method. And actually, we estimated other portions of the Japan now.
Yeah, just along those lines, you might take a look for another subductive zone with a well-defined seismic zone. You might take a look at the Rheology and Hansen 2002 paper where they did the double difference method, and they had a pretty clear double seismic zone in Alaska as well. So that might be nice you could look at also.
Okay.
So how about subducted sediment effect? So you think we'll talk about much about the slab, but the effect of sediment may be more strong until to some depths, I think.
This time we neglected sediment, the presence of sediment. But in case of sediment, the most of hydrous minerals in sediment composition will decompose very shallow part. So anyway, we can apply for sediment composition.
Okay. Thank you. I think we should move on to our final talk in this session.